Good afternoon, everyone. I'm your dear Vidushi, and my PMRF ID is 0602607. Today is the problem solving session second. As in the previous session, we discussed about the electromagnetic radiations and their behavior. That is, they can behave both as a particle as well as the wave nature. So now in this session, firstly, we will discuss about the quantization of energy. So, what do you understand by the term quantization? Quantization means only certain energies are allowed. That is, electrons can have only certain value of energy. Like in hydrogen, the energies that can be allowed are minus 13.6 electron volt, minus 3.4 electron volt, minus 1.5 electron volt, and so on. Suppose these are the different energy levels. This is the ground state. So for ground state energy level, the value of N is 1. Similarly for the above energy levels, N will be 2, N will be 3, 4, 5 and so on. So how do we calculate the energy? The energy can be calculated by using this formula. Here En represents the energy of the nth orbital and it's equal to the minus 2.18 into 10 raised to minus 18 joules per n square, where n can be any integer. So if we substitute the value of n square to 1, then the energy will be equal to minus 13.6 electron volt, and this corresponds to the ground state level. If n will be 2, then it will be 3.4 minus 3.4, then it will be minus 1.5, then it can be minus zero point 0.9 and so on. So the energy is quantized, that is only certain energies are allowed. In hydrogen, there are different spectral series that are Lyman series, Balmer series, Passion series, Bracket, and the Fun series. So basically, what are these spectral series? So firstly, we will discuss about the Lyman series. In Lyman series, the transition is from the higher orbit to the first orbit, that is n equals to 1. Or we can say that there can be transition from n equals to or greater than 2 to n equals to 1. Lyman series are obtained in the ultraviolet region. Now moving to the Balmer series. Balmer series are those in which transition is from higher energy level to the second orbit, that is n equals to 2. And in Balmer series it is obtained in the visible region. Now the third series is the Passion series. In Paschen series, the transition is from the higher orbit to the third orbit, and this series is obtained in the IR region, that is in the infrared region. Now, the next series is the bracket series, in which transition is from the higher orbit to the fourth orbit, and it is obtained also in the IR region, that is in the far IR region. Similarly, the last series is the Fund series. Here, the transition is from the higher orbit to the fifth orbit, that is to n equals to 5, and it is also obtained in the far IR region. So let's see in this diagram, when the transition is from the higher orbit to the first orbit, that is n equals to 1, the first shell, then it belongs to the Lyman series, and it will be in the UV region. Now, if you look at this transition, in this the transition is from the higher orbit like n equals to 5, 4, 3 to the n equals to 2 state, and this series is Balmer series, and it is obtained in the visible region. Similarly, these are Paschen series, in which transitions are from higher orbit to the n equals to 3, the third shell, and this series is obtained in the infrared region. So now let me erase this. Now, suppose these are different energy levels, and if a light is incident here, then the electron will absorb the energy and will be excited to the higher energy level, and here it is unstable, so it will fall back to a low energy level and further emit a light. Now, if we supply light, it should be equal to the difference in the energy levels. Then only transition will occur. Suppose if we supply a light and it does not correspond to the difference in the energy level, if it doesn't correspond to the difference energy level, then there will be no transition. So for a transition to occur, the light supplied should be corresponding to the difference in the energy levels. Now see, in this the energy level diagram over here, n is equals to 1, 2, 3, and so on, and the transition from higher orbit to n equals to 1, it corresponds to the UV wavelengths. From n equals to 5, 4, and 3 to n equals to 2 state, so it belongs to the Balmer region. This corresponds to the Lyman. Now when the transition is from n equals to 5 to n equals to 3 state, or from n equals to 4 to n equals to 3 state, this is Paschen series, and it's obtained in the infrared region. So now we will solve some questions related to this spectral series. So firstly, let me erase this. many stacked line will be observed when the electron jumps from n equals to 5 to n equals to 1 in the visible line spectra of hydrogen atom? So basically in this we have to calculate the number of spectral lines that will be observed when electron will jump from n equals to 5 to n equals to 1 state. So let's draw the spectral lines. Suppose this is n equals to 1, n equals to 2. So from here, how many spectral lines will be observed? Like the transition that possible can be from n equals to 5 to n equals to 1 state, from n equals to 5 to n equals to 2, from n equals to 5 to n equals to 3, from n equals to 5th orbit to n equals to 4th orbit. Also the transition can be from n equals to 4 to n equals to 1 state, from n equals to 4 to n equals to 2, n equals to 4 to n equals to 3, similarly from 3rd to 1st, then n equals to 3 to n equals to 2, and from n equals to 2 to n equals to 1. So these are the different vector lines. So total it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So total there are 10 vector lines. But in the question they've asked how many spectral lines will be observed in the visible line spectra. And we know that visible line means Balmer series. And so what are Balmer series? We already discussed Balmer series are those in which transition is from the higher orbit to the second orbit. So how many transitions are there from higher orbit to the second orbit? So only like this from these three transitions. That is from n equals to 5 to n equals to 2, n equals to 4 to n equals to 2, n equals to 3 to n equals to 2. That is n equals to 5, n equals to 2, n equals to 4 to n equals to 2 and n equals to 3 to n equals to 2. So only these three are observed in the visible line spectra. So total, how many spectral lines will be observed? 3. So let me erase this. So moving to the next question, what is the ground state energy of the hydrogen atom? So the answer will be 13.6 electron volt. So how do we calculate it? We have already discussed. Like ground state means n is equals to 1. And we know that energy formula is minus 13.6 electron volt divided by n square. And we know that for ground state the value of n is 1. So it will be minus 13.6 electron volt. So the correct answer will be minus 13.6 electron volt. So moving to the third question, find the wavelength of radiation emitted from hydrogen atom when electron jumps from third orbit to the second orbit. And the value R is given by 1.097 into 10 raised to the 7 meter inverse. So how can we calculate the wavelength of radiation emitted here? There is a formula to calculate it, that's 1 by wavelength is equals to R into 1 upon n1 square minus 1 upon n2 square. So here in this formula R is Rydberg constant. So now substitute the value. The value of R is already given in the question. So in the question it's from third orbit to the second orbit. So value will be 3 and 2. So what will be the answer after solving this? The answer turns out to be 6.5 into 10 raised to minus 7 meter. Now moving to the next question. Determine the energy that must be given to a hydrogen atom so that it can emit second line of Balmer series. Basically in this we have to calculate the energy. And we know the formula of energy is E is equals to h mu that's equal to hc by lambda. So for this equation, we know the value of h and c, and the value of wavelength we do not know. So we have to calculate first the value of wavelength. So lambda will be equals to, like, this formula, 1 by wavelength is equals to r divided by 1 by n1 square minus 1 by n2 square. So here what will the value of n by n2? Now in the question they are asking about the second line of Balmer series. We discussed earlier in Balmer series the transition is from higher orbit to the second orbit. Here n is 3 and here is 4. So we have to calculate the second line of Balmer series. First line will be from n equals to 3 to n equals to 2, and second line will be from n equals to 4 to n equals to 2. So substitute the value here, 1.097 into 10 raised to the 7 divided by 1 upon 4 square minus 1 by 2 square. So what will the value here? So now if you will calculate the value, by this we can obtain the value of wavelength, and if we will put the value of this in this equation, then we will calculate the energy. As we know, energy will be equal to 6.626 into 10 raised to minus 34 into 3 into 10 raised to power 8 meter per second, and the wavelength value that we calculated from here. So the energy will be 2.55 electron volt. Now we have to calculate the wavelength of electromagnetic radiation emitted by a hydrogen atom which undergoes transition between energy level of minus 1.36 into 10 raised to minus 19 joule and minus 5.45 into 10 raised to minus 19 joule. So how we calculate the wavelength? Energy is given like here. Like the transition between energy levels are given. So the next question is this one. So here we have to calculate the wavelength. We know this formula, energy is equals to minus 13.6 electron volt divided by n square. So we can calculate the value of n by dividing minus, let me erase it, just it will be minus 1.36 into 10 minus 19 equals to minus 13.6 electron volt divided by n square. So the value of n will be turned out to be under root minus 1.36 into 10 minus 19 divided by 13.6. Similarly, for another n, it will be like another energy level. Transition between energy level is this minus 5.45 into 10 minus 19. So it will be under root minus minus 5.45 into 10 minus 19 divided by 13.6. So by solving, what will the value here? It will be approx 2 4 here. It will be approx 4. Now we know this formula. This will be n2, this will be n1. So by substituting the value, one upon 4 square minus 1 by 2 square. So after solving, the wavelength value will turn out to be 4.84 into 10 raised to power 7 minus 7 meter. Now moving to the next, Heisenberg uncertainty principle. So what do we understand by Heisenberg uncertainty principle? Heisenberg uncertainty principle states that it is impossible to measure or calculate exactly both the position and the momentum of an object. If delta x is the error in position measurement and delta p is the error in measurement of momentum, then delta x to delta p should be greater than or equal to h upon 4 pi, where x is the error in position measurement and p is the error in momentum. Also, we know that momentum is equals to mass into velocity. So we substitute the value here, then it can be delta x into delta mv is greater or equal to h upon 4 pi. Now there's some questions related to Heisenberg uncertainty principle. So the first question is, an electron's position can be measured to an accuracy of 10 minus 9 meter. How accurately can the velocity be measured? So how we will solve this? So velocity we have to calculate, it will equal to h by 4 pi into delta x into m. So now substitute the values. And we know for electron the mass is 9.11 into 10 minus 31. So from here we can calculate the value of del V. So the velocity will be 1.16 into 10 raised to 5 meter per second. Now moving to the second question. Position of a chloride ion on a material can be determined to a maximum error of 1 micrometer. If the mass of chloride is 5.86 into 10 minus 26 kg, what will be the error in its velocity measurement? So when this mass is given, position is also given, we have to calculate for the velocity. So we know the formula now. Velocity will be equal to h upon 4 pi del x into m. Now substitute the values. We know that 1 micrometer is equals to 10 minus 6 meter. So by solving, we will get the value of velocity. And the value will be, sorry, just a second. So the value after solving will be 9 into 10 raised to minus 4 meter per second. So just you have to remember the formula that del x dot del p should be greater or equal to h upon 4 pi. This formula. Now there is another question. In a certain atom, an electron stays in an energy state for 4 into 10 minus 12 seconds. What is the uncertainty in the energy of electron? So now you have to calculate the uncertainty in the energy. So for energy, there's a formula. So now we know the value of h and t and substitute it to get the value of uncertainty in energy of the electron. So after solving, the value will be 1.318 into 10 raised to minus 23 joules. So basically, there are two formulas that you have to remember for Heisenberg uncertainty principle. The first one is this, and second one is this. Now there are other questions. A 150-gram baseball traveling at 220 meters per second measured to an accuracy of 0.065%. Calculate the uncertainty in position of a baseball. So here you have to calculate x. So for x, we know the formula. So it will be 6.626 into 10 minus 34. So like mass is in grams, so we'll convert it into kg. It will be 150 by 1000. That will 0.15 kg. And for velocity, it's given 220 meter per second to an accuracy of 0.065%. So we just multiply it 220. So by solving this, we calculate the uncertainty in the position of a baseball. So what will be the answer after solving this? So the answer will be 49.188 into 10 minus 34 meter. Now moving to the next question. Determine the minimum uncertainties in the positions of the following objects if their speeds are known with the precision of 1 into 10 minus 3 meter per second. So first we have to calculate for electron and then a bowling ball of mass 6 kg. So I'm giving you time to calculate it. Firstly do for an electron. You have to calculate uncertainty in the position means del x. It's uncertain position. So from here we calculate the value of uncertainty in position. So it will be 0.1158. Right. So now let me erase this. Now we have to calculate for the bowling ball of mass 6 kgs. So how we will do this? Same formula we have to apply. So by solving this, we can calculate the value of uncertainty in position for a bowling ball. And by solving, the answer will be 0.71756 into 10 minus 31 meter. So these all were the questions for the Heisenberg uncertainty principle. Now moving to the next, wave function. So what do we understand by the term wave function? A wave function gives the probability of finding the particle at a certain location. The square of the wave function psi square at a point is proportional to the probability of finding the particle at that point. That is psi square is equals to psi star psi greater than or equal to 0, where psi star is the complex conjugate of psi. So basically, what are the properties of a wave function? So it should be continuous, it should have a single value. Also, the probability of finding a particle, if it exists, it's 1. Probability distribution in 3 dimensions is established using the wave function. So now what do you understand by commutators? A commutator in quantum mechanics tells us if we can measure two observables at the same time. If the commutator of two observables is 0, then they can be measured at the same time. Otherwise, there exists an uncertainty relation between the two. So, suppose there are two operators, A operator and a B operator. So, for commutator, you will represent in the square brackets. So, How do we know that this will commute with each other? If A operator and B operator is equals to AB minus BA, if it will be 0, then it will commute, otherwise it will not commute. Now there is x position operator and d by dx. We have to calculate whether it will commute, these two operators will commute or not. So how we will do? We already discussed, it will be x d by dx. We always have to multiply by a wave function, that is psi. X d by dx minus d by dx x multiply by wave function. So it will be x d psi by dx minus d x psi by dx. So here there is only one operator, so it will be as it is. Here there are two operators. So when these two operator, how we can solve it? We can solve by writing first operator, then differentiation of second, minus first operator, differentiation of second. So these two terms will exit calculus will be cut out. So we know differentiation of dx by dx is 1, so it will be minus psi. So we will remove the psi, it will be x comma d by dx equals to minus 1. So value is not 0, then it means it will not commute. So now we will erase it. Now we have to calculate whether x in px will commute or not. X is the position operator and p will be the momentum operator, and we know the value of px, it will be equal to minus iota h cut curly by curly x. So here x operator comma px it will equal to so substitute the value of px here. So there is nothing to evaluate here. Am I right? It has px only, this term is px only, minus minus will be plus. Just a second. And we know this will be 1, so it will be xpx plus iota h cut. So this will also not commute as it is not 0. So up to this it is clear. Now we will solve another example. Here x and h, where x is the position operator and h is the Hamiltonian operator, and for Hamiltonian operator it is equals to the kinetic energy plus potential energy. So how we will solve this? It will be x it will be equal to x comma t plus v, or we may write it as x plus t, x comma t plus x comma v, where t is the kinetic energy and v is the potential energy, and this we know that it is equal to 0. So it will be x comma p square upon 2m. We know that kinetic energy is equal to p square upon 2m, as 1 by 2m is constant, so we will also write it as like this. So how we will solve it? We will write it like that: 1 by 2m p x comma p plus x comma p dot p. We know that it is equals to iota h cut, this value. So 1 by 2m p iota h cut plus same here iota h cut p, so it will be equal to 2 times of iota h cut p by 2m. So it will be iota h cut p by 2m. So is it clear? So now let me erase this. Now, now we have to calculate the value of commutator of px with ly. You know the value of px, it will be minus iota h cut curly by curly x. Now ly is angular momentum. You have to calculate, you know, L is equals to R into P. So write L, it will be equal to Lx I cap plus Ly j cap plus Lz k cap. Similarly, R it will equal to Rx I cap plus xi cap plus yj cap R plus zk cap. As L is equals to R into P, so P will be now Px I cap plus Px plus Py j cap plus Pz k cap. So it will be like so z I cap j cap k cap and a Px Py Pz. So what will the value of L? It will be just for like I cap, it will be multiplication of this minus of this. ypz minus zpy I cap minus for j cap it will be xpz minus zpx. For k cap it will be xpy minus ypx. So what will the value of L y? It will be this. So now you can calculate the value of the commutator of px and y, and it will be iota h cut px. This one. Is it clear now? I will repeat one more time. Like if you have to calculate the value of commutator of px with ly, you know that px is minus iota h cut curly by curly x, sorry, and L is angular momentum is equals to r into p. So r will be x I cap plus y j cap plus z k cap, and p will be px I cap plus py j cap plus pz k cap. So now what will be the value of L? For I cap it will be multiplication of y pz minus zpy, and for j cap it will be minus xpz minus zpy. Then for k cap it will be plus zpy minus xpy. So now this value will be corresponding to Ly. Now you can put the values and find whether what will be the value of commutator, and it will be iota h cut px. Now I will erase it. Now we will solve some questions. The This symbol is of which operator? Laplacian, dot energy, potential energy, and vector. So this symbol is for the Laplacian operator. Now what will be the probability of finding a particle in space? Infinite, 0, unity, less than 1. So it will be unity. So next question. Which quantum number is not related with the Schrodinger equation? Azimuthal, principal, magnetic, spin. So what will be the answer? It will be spin. So next. Balmer series arises due to transition between n equals to 3, 4, 5, or infinity to n equals to 2, n equals to 3, 4, 5 to n equals to 1, n equals to 4, 5, 6 to n equals to 3, n equals to 2 to n equals to 3, 4, 5. So what will be the answer? Palmer series are the series in which transition is from the high orbit to second orbit. The correct answer will be this one. Moving to the next question. Which of the following is not correct about the wave function? It must be single valued. Its single derivative must be single valued and continuous. It must be square integrable. It can take more than one value at a point. You have to calculate that is incorrect. So what will be that option? It can take more than one value at a point. Now moving to the next question. Probability density is defined as wave function, square root of wave function or square of wave function. So it will be square of wave function. Now we have to calculate the ratio of population of the two states in helium neon laser that produce light of wavelength 6328 Armstrong at 25 degrees Celsius. I'm giving 2 minutes time to solve it. So the formula for this will be N2 by N1 is equals to E minus del E by KT. So you have to calculate the population of these two states. So it will be E minus delta E by KT. You have given wavelength. So for this equation you need the value of energy. So firstly we calculate the value of energy by using this equation is equals to h mu, that is hc by lambda. So if you will substitute the values here, it will be 6.626. Then wavelength is 6328 Armstrong. So to convert Armstrong into meter, we multiply by 10 raised to power minus 10 meter. So by solving it, the value of energy will be 3.143 into 10 minus 19 joule. Up to this, is it clear? So K will have value 1.38, 10 minus 23, and temperature it's in 25 degrees Celsius. So convert it into Kelvin by addition of plus 273, then it will be in Kelvin, that is 298. So by solving it, the value will be 1.1 into 10 minus 33. So this will be the ratio of population of the two states. Now the next question is, calculate the ratio of population between two states at 300 Kelvin if the gap between them is 4.1936 into 10 minus 21 joule. So how we will calculate this? And giving just 2 minutes time for calculation. So what will be the answer after solving this? It will be 0.363. So I'll first erase this. Now moving to the next question. The uncertainty in position of a ball is given which is traveling at a speed of 20 meters a second. Mass of the ball is 0.5 kg. Calculate the uncertainty in its momentum. So I'm giving 2 minutes time. Just calculate it. So you know the Heisenberg uncertainty principle. Here you have to calculate the uncertainty in the momentum. So the formula is del x del p is equal to h upon 4 pi. So for del p is equals to h upon 4 pi del x. So it will be equal to 6.626 into 10 minus 34 upon 4 into 3.14 into 5.29 into 10 minus 30. So by solving it, you will calculate the value of uncertainty in momentum. So what will the value after solving this? Or you can also solve like, you know, you have to just calculate the momentum. This is mass into velocity. Mass is 0.5 kg and velocity is 20 meter per second. So it will be 1 into 10 minus 6. The certain position, momentum. Now, what is the Doppler shifted wavelength of a red 680 nanometer traffic light approached at 60 km per hour? So for this, we have to use this formula. Delta lambda upon lambda naught equals to V by C. Where what's this? This is change in wavelength. Lambda naught is the emitted wavelength. V is the relative velocity of the source and observer. and this c is the speed of light in vacuum. So change in wavelength we can write it as lambda minus lambda naught. Lambda is the observed wavelength. So lambda can be written as lambda naught v by c plus lambda naught. So what's the lambda naught? Lambda naught, you know the value, it's 680 nanometer. So it will be 680 into 10 minus 9 meter. Or you can also write as 6.8 into 10 minus 10. Or you can write as 6.8 into 10 minus 7. What's v? V is the relative velocity. You know it is given as kilometer per hour. So you have to convert it into meter per second. So it will be 16.67. And you know the speed of light plus lambda naught at 6.680 into 10 minus 9. So what will the answer have to solve in this? So the answer will be 680.00038 nanometer. So in this way you will calculate the Doppler shifted wavelength. So now what we have discussed from starting, we'll just revise it once. Firstly, we have to remember this formula to calculate the energy. Like if I will ask about like minus 3.4, so you should know like it corresponds to the first excited state energy level, like to minus zero point 0.9 it corresponds to third excited level. Then all this Lyman, Balmer, Paschen, Brackett and Fun, these are the hydrogen spectral series, where Lyman series is obtained in the UV, Balmer is obtained in the visible, Paschen is obtained in the IR, while the Brackett and Fun series are obtained in the far IR region. Then what is the formula for calculating spectral line? You can also, I've discussed earlier, but there's also one formula. It's N2 minus N1 multiplied by N2 minus N1 plus 1 divided by 2. So here it's asked from n equals to 5 to n equals to 1. So n2 is 5, well, and 1 is 1. 5 minus 1 is 4. 4 plus 1, 5 divided by 2. 20 upon 2, that is 10. So by this formula also you can calculate the number of spectral lines. But in this question it was visible line, that's why the answer is 3. Just remember this formula to calculate the number of spectral lines. It's n2 minus n1 multiplied by n2 minus n1 plus 1 divided by 2. Then you should know this formula to calculate the wavelength, that 1 by wavelength is equals to r 1 upon n1 square minus 1 by n2 square. And r will be the readable constant whose value is 1.097 into 10 raised to 7 meter inverse. Then you should know about the Heisenberg uncertainty principle. Like it states that it is impossible to measure or calculate both the position and momentum. And there are two formulas for the numerical. So, like first one is this: the uncertainty in energy and time, it should be greater than or equal to h upon 4 pi. And the second formula is uncertainty in position and uncertainty in momentum. It is greater than or equal to h upon 4 pi. Where you can also substitute the value of p, as p is equals to mv. The formula can be uncertainty in position is equals to be del x m dot del v greater than or equal to h upon 4 pi. So these two formulas you should remember for solving. Then we discuss some questions related to this. Then about wave function. So what do you understand about the wave function? And what are the properties of wave function? That it should be continuous, it should have single value. Also the probability of finding a particle if it exists is 1. Then we discuss about commutator. Like suppose if there are two operators A and B, so how can they commute? They can only commute if AB minus BA will equals to 0, then only it will commute. If it will not be equal to 0, then it will not commute. So commutator tells if we can measure two observables at the same time. And we also discuss some of the questions related to this. Then what's the formula to calculate the ratio of population of two states? It's n2 divided by n1 is equals to E minus del E by kt. You should remember the value of k, that is 1.38 into 10 minus 23, and also the temperature should be in Kelvin. So to convert degree Celsius to degree Kelvin, you just have to add plus 273 to it. Then we discuss about Doppler shifted wavelength. So it is given by this formula where lambda will be observed wavelength, lambda naught will be emitted wavelength, v will be the relative velocity of the source and the observer, and c will be the speed of light in vacuum. So that's all for today. Thank you.